Good morning, good afternoon, good evening, good whatever you are, and welcome to this SNIA Cloud Storage Technologies presentation on why composable infrastructure. We've got a really interesting talk for you today, but before we get into the talk itself, just let me run you through the interface if you're not familiar with it. First of all, you have the ability to make that screen as big as the entire desktop. There's a button there that allows you to expand out, and that's just in case we have slides that are perhaps a little dense or perhaps you can't see the detail in them, and you can make them bigger and see exactly what's going on. Secondly, we have the ability for you to ask questions during the presentation. Please do so. Those questions we'll attempt to answer as we're presenting today, and if we don't get to them, we have a blog that I'll point you at the back end of the presentation where we'll answer all the questions that were asked and put them together in a sensible format so that you can see them online if you wish to go to the website. And last but not least, you have the ability to rate us as you leave the presentation on a scale of 1 to 5, where 1 is, I wish I'd been doing something else, to 5, great, I want to hear more about this. So if you'd like to rate us on the way out, we'd be immensely grateful, because it does give us an indication of whether we're bringing you the right subjects or not, and any comments you might have about the presentation itself, we'll take those on board and attempt to be much better at it the next time if you've got criticisms, or take the applause if you think that we've done a really good job. So without further ado, let me introduce today's presenters. We have Philip Kufelt, who's from the University of California, Santa Cruz, or as I'm going to show at UCSC. Good morning, Philip.
Good morning.
We're also joined by Mike Jochimson, who is the works for Caminario. Mike is in Boston today. Hello, Mike.
Hello. Thanks, Alex.
And myself, I'm Alex McDonald from NetApp, and I'm your top tailor for today. I'm your host for today. So, about this presentation is copyrighted by SNIA unless otherwise noted. There are some other copyrights held by other organizations you'll see in here. But the essence here is there are two things. First of all, please, please, please observe our copyrights. And secondly, there are no warranties expressed or implied with this. This presentation is without risk to us. And if you need to get a lawyer involved, then get a lawyer involved with somebody else, because we'll not be responding. Usual legal disclaimer. You're on your own. However, this presentation also contains some forward-looking statements, because we're talking about technologies that are coming down the pipe. Not that far away, as the little graphic says on the right-hand side. But it does contain some forward-looking statements, and in particular, it's an intelligent, hopefully, and educated exposition of this new approach, composable infrastructures, to compute, networking, and storage technology. Secondly, we're going to be talking about third-party technologies, organizations that are putting together programs that and standards that allow us to do composable infrastructure. And these are our interpretations of their technologies. We're not speaking for them or on behalf of them. We're speaking about them. And thirdly, I hope you understand a little about how compute, networking, and storage are currently bolted together, whether it be NAS or SAN or hyperconverged, because we're going to be talking about the next phase of what we think is coming down the pipe in terms of screwing together those particular parts of technology. So with that being said and done, SNIA is 185 leading industry organizations that are focused on storage and networking. We've got about 2,000 active contributing members and about 50,000 IT end users and storage pros worldwide, of which you are one. The things that we do in the CSTI, we changed our name last year from Cloud Storage Initiative because we thought cloud storage was a one war. There really wasn't much more to talk about cloud storage. Cloud storage technologies, how you go about screwing it together and managing it, is much more interesting. So that's what we're called nowadays, the CSTI. And our business is to educate, to support and promote, to understand and to collaborate, and to provide you with quality end-user education about where we think the storage industry is at and where it's going. So without further ado, this is today's agenda. It's a pretty simple agenda. We're going to talk about composable infrastructure. And first of all, Philip Kufelt is going to talk about what's driving this current compute network and storage development environment that we're living through. And then Mike will talk about composable infrastructure itself and explain what it is. And then lastly, right at the back end, Philip will again talk about what we're doing to realize it and some of the technologies that are already in place, and I'll wrap up. So without further ado, Philip, over to you.
Thanks, Alex. So today you'll see a description of what composable infrastructure is, and you'll see that it's a pretty radical departure from the way that we currently build systems. And I wanted to take the first part of this presentation and kind of go back to some simple principles and talk about how are we getting to this sort of radical change. What's prompting us to want to change the way that we build our infrastructure. And so I'm going to go through some historical viewpoints and also some very simplistic descriptions of things that we all have a strong familiarity with. For example, what is an application? I think the root of all of this starts with the application and the growth of applications today, so talking about them is, I think, important. An application is a very simple thing. It's a computational task that we create to accomplish some sort of service that we're providing. And it has requirements such as needing a system. A task needs a system in which to run on. Traditionally they have been, based on just several components, a processor, some memory, some network, and ultimately some storage. And each application comes with its own set of requirements. How much processing power it needs, how much memory it needs, what kind of bandwidth it needs out of the network, what's its location, how do I access that task, and availability. Do I restart my applications when they fail, or do I have multiple versions of the application running to provide a higher level of service? And the stores too have that similar requirement of bandwidth, latency, capacity, and availability that you have to fulfill when you're building a system to support an application. So over the last 30 or 40 years, we have seen some very distinct errors about how we build systems to support these applications. And during those periods of time, we have seen applications growing geometrically. Now, I have to admit that this chart that I'm showing you right now has no real basis in numbers. It's just sort of an agreement that we have seen a pretty large application growth over the course of the last 30 or 40 years, and it is continuing to grow as we move into the cloud era at a pretty staggering pace, to the point where we're having hundreds of thousands of applications running in the clouds at any given time, if not millions. And they're growing really, even faster than technology. That is, that the ability to host these applications, the number of applications is outstripping our ability to host them, which means that our data centers are growing in size continually through generation after generation of hardware. And because of that, we have more and more hardware showing up in the data center. We're seeing the applications get more varied on what they do, from typical storage service providing to database to machine learning. We're now seeing lots and lots of varying applications that have really diverse configuration requirements. And it also has a growing management problem. The more applications there are, the more systems there are, the more of a management problem we have. And we've seen over this time frame that flexibility and cost have really been driving our direction in the hardware arena, trying to find ways as we move through this curve of ever-increasing applications to try to reduce over-provisioning, to reduce cost as we move forward. We've also seen disaggregation helping with the management problem. We saw that in the 90s in the beginning of the client-server era, and then through the 90s into the 2000s of, with SAN and NAS, being able to focus the management problem on small numbers of servers rather than having storage management problems on all servers. So disaggregation allowed us to focus the management problem. As we continue to move through this, let me kind of give an example of how a shift, reduced the allocation or the over-provisioning. For example, when we were in the mainframe days and we had a mainframe that was running, n applications, and we needed n+1 applications, you had to buy another mainframe, and that unit of allocation was really just too big, and it drove the idea that if we had smaller systems that we could layer apps on top of, we would have more flexibility and be able to allocate hardware on an as-needed basis as our applications grew at a much finer granularity at a much cheaper cost. And that gave us better control over the configuration because we could tailor the individual servers to an individual app. We could also get availability by distributing our apps across many pieces of hardware, getting better availability. And this continued along, and we saw our hardware grow faster and stronger over that time, and we began layering many apps on top of a single server until we got to a point where our application load was growing at such a rate and was so dynamic that we were hitting the needs of elasticity, the ability to, deploy many apps at a moment's notice and then possibly undeploy those apps as service requirements changed. And trying to buy these large systems to support this was getting an ever-increasing cost burden. So we looked to the cloud to try to support that by allowing us to change the unit of allocation away from the server to the app. I merely scheduled when an app should run, and the cloud took care of where it should run and how it should run. And that gave me a lot of benefits as far as elasticity and location abstraction. It could run anywhere close to my clients on the planet. It gave me a lot of advantages. However, underneath the scenes, in the cloud itself, we have the same problems. These cloud environments are essentially collections of large server boxes that are running all of these applications. And they have the similar problems that we saw in the end of the client-server era. At the same time that this was going on, that we were moving from timeshare to client-server to the cloud, we saw a lot of changes in our hardware that really kind of dictated how we allocated and created our servers. During the 80s and 90s, we saw the tremendous Moore's Law type of growth, where we were seeing a doubling of compute power every year and a half, such that from one generation to the next, you were getting twice as much computer as you were in the previous generation, and you could easily end-of-life old equipment because the new equipment was so powerful we could layer our applications on top of that newer equipment. However, as we moved through into the 2000s, we started to see Dennard scaling ending, which is essentially the law that states that you can continually get power savings as we scale up the cycle of the CPUs, such that we can get these doubling of clock cycles on our CPUs in the next generation without heating problems and other things of that nature. So we went from 500 megahertz to a gigahertz type of processors as we moved from generation to generation. However, as we got further down the line, we started to see power leakage and heat in these processors that prevented that from happening. So we started to see the decline of the increases in CPU clock cycles. So how did we get our power after that? Well, we started adding cores to the systems to increase the amount of computational power in a single processor. But eventually you hit the limits of that as well because, you can only, according to Amdahl's law, you can only parallelize an app so much and then you're bounded by how parallelized a service can be and how many cores it could actually utilize. Furthermore, the more cores you have on a system, the more applications start competing for resources that don't scale that way, such as memory. And I'm going to talk about that on the next slide. But we saw a slowing down of the core counts. And now we're starting to see the end of Moore's Law. We're starting to see the end of the ability to shrink the transistor, showing that we're not going to see doubling of power for, at a 3% rate, sort of every 20 years will we see this. So what's left then? What are we doing now to try to, keep some of this performance gains going? Is that we're creating domain-specific architectures. You can see it in the past. For the last 20 years, we've had graphical processing units that focus the graphical load on a particular processor for handling. We've also seen it with offloading smart network interface controllers that allow you to offload your network stacks onto the actual NIC itself. And now we're starting to see this in the AI and machine learning world. Specifically in AI, Google produced the first TPU, which is a tensor processing unit, which is specifically for AI applications. And they were able to see, a doubling of performance and a reduction in power, significant reduction in power for these TPUs. And we're also seeing it in the storage world with FPGA-based accelerators, where you create an accelerator that sits in front of your storage that improves the performance of your database application because the I/O path is understood, and you can create sort of fast paths for these particular applications. And these are essentially extending out our growth of our systems, but they're increasing complexity, increasing configuration complexity, in the sense that now my AI applications require TPUs, or my machine learning applications require GPUs. My databases require a FPGA-based accelerator. And so now the server configuration gets more and more complex. Additionally, there's one other problem I want to raise here, and it's a problem, and it's also a blessing. Once again, I want to thank Fritz Kruger and Alan Samuels for bringing this to the world. They did a great presentation on the worrisome DDR trend, which shows they plotted the growth of network bandwidth and flash bandwidth against the growth of DDR bandwidth. And what they showed is that we are in a phase right now of geometric growth of our flash and network bandwidth, but we are at a much smaller growth rate for our DDR bandwidth. And what does that mean? Well, that means that as we add flash devices and network cards to our systems, we're now using up a larger chunk of the DDR bandwidth for I/O processing. And in a typically, tuned system, you would expect your I/O processing to be around 20 or 30%, which means that with, modern day flash devices, you're getting to the point where, 3 or 4 SSDs will reach that limit on a per proc basis, right? So we're seeing more and more competition for the DDR bandwidth from our I/O subsystems, and our applications are taking advantage of this. Our applications want this speed. So the ability to layer more and more apps on top of these big multi-core systems is getting capped by this bandwidth problem. It also might mean that the age of hyper-converged infrastructure may be closing, because that's an extreme example of layering a bunch of different applications, not only your user applications, but your storage management applications on the same system. I'll talk about the blessing of this problem in the future, but the real blessing comes from the fact that our networks are getting faster. We'll talk more about that in a bit. So now what does our tasks, our applications look like today? Well, it's now far more complex than it was 20 years ago. Not only do you have proc memory and network and storage, you have all sorts of other flavors of components that need to be there for the application. So applications may use CPUs or SoCs, they may have different core count requirements, they may have DDR capacity and performance requirements, different NIC requirements, but now they have accelerators, GPUs, TPUs, and there will be other domain-specific hardware options going forward into the future. Storage is really proliferated as well. We are seeing, not only cold stores, but we're seeing differing styles of HDDs, and the flash world has just blossomed into many, many different options, ranging from performance to different capacities to different latencies. But in addition to that, we also have seen the rise of persistent memory devices showing up. These devices, although they look like storage devices, are akin to memory with regard to performance. So they show similar type of bandwidth and latency to regular DDR, but in a storage form. And all of these components have to go in a box. We have to figure out how to pack a server with these components, and it's all dictated by app requirements, and these app requirements are varied. What and how much is decided at purchase time, so once you've acquired it, there's no going back. There's no evolution of that system. That system is now deployed, and you're not going to change it, which is part of the problem. So here's really where the problem lies. The application requirements are wide and varied. They have a complicated set of hardware requirements, and understanding how to have the right systems for every application is getting more and more difficult because you have to map these requirements onto physical hardware. Due to core counts, if you want to get efficiency out of your system, and this is actually one of the core issues that I think we're going to be faced with going forward, is how to get efficient use of our hardware. As hardware is not dramatically improving over time, we're going to be getting more and more hardware. We want to take advantage of that hardware over a longer period of time in a more efficient manner. You have to layer multiple apps, and you have to be able to understand how those apps will use that hardware and how efficiently will they take advantage of the resources you have put into that box. And this forces IT managers to become system designers, in effect. They have to understand the apps and the app requirements, and then understand how they will interact with each other on the box to get the efficiencies that they're looking for. And what ends up happening is you end up having IT managers that end up over-provisioning inside the system to compensate for unknowns, and that increased cost, basically. You also have, the more apps that you have on a system, the more availability and competition issues you're faced with that you have to understand. Application requirements are constantly evolving and changing. If you told people about our machine learning and AI requirements even 4 years ago, you would have been thought to be crazy, but they're here now, and they have strong requirements on our hardware. Requirements can ramp up as easily as they can be restricted back. As applications age, the number of people they're serving may change, and it may have less requirements on the system. So what ends up happening is that these evolving requirements invalidate the original system design requirements, and again, you're having a harder time getting efficiency out of these boxes that were bought 2 and 3 years ago. The growth rate of apps is still continuing. We're still continuing to grow our data centers, which forces us to, again, over-provision on the server boundary for elasticity. And this ever-growing classes of hardware systems. I'm going to be creating systems for my machine learning. I'm going to be creating systems for my AI, for my database, for my storage management. I have these classes of hardware that are growing that I have to manage, and I have life cycle management where I have to not only acquire them, but I have to scale them over time, manage them while they're up and running, and then EOL them at some point. It becomes a very difficult multi-vectored problem. So I think what this points to is that using the multi-core server as the unit of app allocation is now too big and too complicated, and we need to find ways of trying to reduce the size of the unit of allocation to more closely meet how we schedule our apps and utilize them. So what would something like that look like? Well, and this is, just kind of an idea here is that around building enclosures full of components such that I can, interconnect these things so that they're all connected via some sort of fabric. And this type of interconnect and enclosing of components would allow me to dynamically select components to wire together, if you will, through software, right? Utilizing the hardware fabrics that are in between them, I use software to essentially allocate CPUs and GPUs and memory to create a virtual system. And so this is the kind of goal that we're headed for, is that the unit of allocation becomes the component. And it allows me to dynamically create systems that meet the needs of an application or set of applications, but then just as easily tear it down and change it as my application requirements change. So if an application suddenly needs 5 GPUs instead of 1, I can allocate those and add those to an existing system dynamically. We're already moving this way. We have been moving this way for some time. We have been doing it with software-defined networking, where we create virtual networks dynamically through software. No longer are we pinned down by the hardware and how we wire these things up. Software-defined storage has done the same thing by disaggregating the storage away from the server, creating NAS and SAN initially, but now we have scale-out. And we also have NVMe over fabric devices that allow us to create pools of NVMe devices that can be allocated and deallocated on an as-needed basis. We're seeing these persistent memories show up on the fabrics as well, just like the NVMe over fabric devices. And we're seeing storage accelerators show up on the market today, that provide SoC or FPGA-based acceleration, but sit on a PCI network that is, essentially a fabric that allows me to interconnect them to servers on a dynamic basis. So this is kind of the direction we're moving in, and I'd like to hand it over to Mike now to talk more about what composable infrastructure is. Mike?
Yep, thank you, Philip. So in the industry, when a new concept or technology emerges, we generally find ourselves faced with a definitional issue. And generally that means that the early definition is written by the early entrants into the market. In other words, the truth can be developed by the leaders to the market. But over time, as other entrants come into the market, you start to see the varied definitions boil down to a general set of generic and all-encompassing factors. But with composable infrastructure, I'll suggest that we're closer to the early definition than we are to the final definition. So in the absence of a true all-encompassing definition, I'll fall back to the source of all truth, not Google, Merriam-Webster Dictionary. And if I look at the root of composable infrastructure, you have the concept of composability, to compose, form by putting something together, and infrastructure, the underlying foundation or basic framework of the system. And that proves to be a good, very general definition, but it really doesn't give you enough information to make a rational decision about what composable infrastructure is and how you would go about purchasing and implementing it. So if we look at some of the definitions that are beginning to emerge in the industry, I took a few samples here, and I know this is a lot of words on a page, but taking some of the articles that are out there from Network World, ZDNet, IT Pro Today, and there are a number of others, but these start to show you a few of the concepts in common between definitions emerging out in the market. And so you can see here that the concept of the components of composable infrastructure being compute, storage, and networking, as Philip described earlier, that these are logically pooled on the network or fabric, that they can be provisioned or composed as needed, that the composition needs to be API driven, and that it needs to be driven by the requirements of the application. So again, we're starting to see some of the commonality in definitions that are emerging. And if I take that and expand on that a little to some of the between the lines implicit requirements, again, you have separate compute, storage, and networking components. These are pools of resources. They don't need to be physically proximate in order to be composed. They can be composed as needed via an orchestration layer, which implies software. And this becomes a very critical component of the overall solution, and one where we're seeing a lot of work going on in the industry. Scalability in this environment is not a one-way street. And Philip talked about this, that the application drives the scalability of the system. And therefore, scalability has to be both up and down based on the current needs of the application. And by the way, it's dynamic, so as the application changes, the system needs to be scaled accordingly, up or down. And so the API becomes important because in order for this to happen autonomously, that orchestration layer needs to have access to all of the components, both their attributes and their control layers, so that it can modify the concept of the system. And again, this is all driven by the needs of the application. So if we revisit the concept of disaggregation that Philip talked about earlier, and he'll go into more detail on this again later, there are really two levels of separating the system into the component parts. At the high level, the separation is between the compute, network, and storage, as the current definition of composable infrastructure stated. And this is really the current state of the solutions that are available and emerging into the market today. That ability to discretely pull compute, network, and storage components at a high level into a virtual definition of a system. And the future is the separation of those components into the subcomponents that you can see in the picture that is here on the left and that Philip showed earlier, down to the subcomponents of a compute, a storage, or a networking layer. So the future looking work in the industry is looking at composability down to that subcomponent level and orchestrating virtually anything which can be accessed on the network. So what about virtualization and containerization? Isn't this a way to solve the issue and be able to share these resources? And while that's true, they're fundamentally coming at this from the opposite approach, where both of these technologies are taking the concept of a single system and sharing it amongst multiple applications, if you will. So they both deal with one instance of a component, for example, a server in a server virtualization environment, and dividing it between those multiple applications. And while virtualization and containerization may be fundamentally different about how they sit on top of those resources and provision it, they're both starting from the same premise of taking that single environment and sharing it. And by the way, this doesn't mean to imply that there's mutual exclusivity between virtualization, containerization, and the concept of composable infrastructure. They can happily coexist if it's done right. So this might explain it a little better. And if you look at the left, virtualization and containerization are taking this concept of a full glass of orange juice and making it look like multiple glasses of orange juice to multiple thirsty individuals, each individual thinking they have the entire glass of orange juice. And it's determining the needs of each individual, and then it provisions them the size of glass of orange juice with straw and slices of oranges from a single glass based on their needs. And this assumes that no individual individual's needs exceed the capacity of the single glass. And in fact, this approach shines where there's a large number of individuals with small enough needs that they can all share the same glass of orange juice, thinking they each have the entire glass. On the other hand, composability is somewhat the opposite approach, where I take the various components of that glass of orange juice, the orange juice itself, the slices of orange that go with it, and the straws, and based on the needs of the particular individual, how much orange juice, how many slices of orange, and how many straws are needed to build a single glass of orange juice. And this allows them to define what the glass of orange juice looks like based on the thirst or need of the actual individual or user. And because different individuals have different needs, each of them may be presented a different size glass with a different amount of orange juice, a different number of straws, a different number of slices of orange. So this gets to the root of what composable infrastructure is. It's taking those components that make up the whole and allocating them into the virtual definition of the whole based on the explicit needs of the application itself. And as the individual's needs change over time, the ingredients can be scaled up or down based on what their individual needs are today. And that needs to be dynamic in a composable infrastructure environment, which gets back to the concept of some kind of orchestration layer, the software layer, which is moderating the needs of the application and provisioning the composed infrastructure environment based on the current needs of that application. So you can see where we're at today, where we've been. We talked about the virtualization containerization environment, even back to the mainframe environment that Philip started the conversation with, all as ways to serve applications, whether it's a single application with a single environment, multiple applications with a single environment in the virtualization scenario, to where we are today, being able to provision major components, compute, storage, and networking based on the needs of an application, in some cases done autonomously, in some cases the ability to scale up and down. But there's a lot of work going on in this area to build true end-to-end orchestration environments that have the ability to identify the needs of applications and identify those dynamically so that it's not a manual process for a user to plug that in, and then compose and orchestrate the environment automatically based on those particular needs. And where we're going is to take this concept and further explode out the idea of a component, that compute, storage, and networking layer, into the various subcomponents that are all widely available on the network. They may be multiple components within a single component today, but the ability to separate those out and orchestrate those based on the need of an application. And with that, Philip is going to take this concept and talk about some of the work that's going on in the industry, both in standards organizations and other industry organizations, to further explore how we develop that. Philip?
Thanks, Mike. So for all of this to work, you have to have the ability to disaggregate on a component layer. And disaggregation is the key to that. And the disaggregation requires some interconnect that's capable of providing the service levels that we're used to in a modern server environment. And this is, you know, I said previously in one of my previous slides that one of the bad things that was going on was that we're seeing a lot of competition for DDR because our networks and our flash are getting much, much faster. But it's exactly that reason that we can contemplate doing disaggregation, is that our interconnects are slowly catching up to our local interconnect speeds. So when you look at you know, DDR speeds today being, you know, upwards to 25 gigabytes per second or even higher. We're seeing interconnects that are getting up to that rate as well, and that's allowing us to contemplate disaggregating even things like memory. Standards are leading the way in this space, and I'm going to talk about some of those standards efforts that are in place right now. This is a very broad topic with lots of depth as well. So this is just going to be an intro kind of into the names of the standards, and we're going to just kind of skim the surface over the next few minutes. So again, we're talking about understanding how we can interconnect these devices, how we can have a high bandwidth fabric, an I/O fabric, network fabrics. And I think we already know that we have network fabrics that are pretty robust today, allowing us for storage disaggregation. We're even seeing, now with RDMA and the ability to even get latency numbers that look like very similar to local PCIe type of latencies out of our network from our storage devices. But let's look at the I/O fabric itself. One of the examples that's been existing for quite some time is PCIe Express. That allows us to connect our processors directly to our I/O devices, and that has been around for quite a long time. The Intel and AMD processors already have direct PCIe lanes coming direct out of them, so do ARM SoCs. It's got extremely broad support in the server world. It was once only a local interconnect. That meant that the devices were part of the server itself, and once they were deployed, you weren't changing the configuration of those PCIe devices. But over the last 4 to 5 years, switching technology in the PCIe space has enabled creating a fabric. So now I can create enclosures with PCIe devices and have them switched to servers and allow me to configure which servers have which PCIe devices. And this is really getting more important in the storage world, and I'll show that on the next slide. But it is still a target initiator architecture, and this goes to one of the questions that was asked about security in the composable infrastructure world. And one of the things that mitigates, there is security here as in everything with computers. There is security issues. But most of these things are point-to-point type of relationships. They're not shared relationships. So just like a PCIe device is a target and initiator, there's one server that owns it. These point-to-point things are private connections between a server and its device, mitigating some of the security concerns. But there are ongoing work in the standards bodies. I'll talk on a little bit more about that in a bit. PCIe version 4 right now, we're seeing 2 gigabytes per second per lane. So that means an 8-lane device can have up to 16 gigabytes per second. That's really getting up into the DDR, the bottom end of the DDR space. PCIe version 5 is close on its heels, going to be doing 4 gigabytes per second per lane, yielding a 32 gigabyte per second device with 8 lanes. So really fast devices are showing up in the PCIe world that is going to be enabling this disaggregation. However, let me go back a slide and say one thing. PCI Express doesn't do anything with regard to cache coherency, and that's one of the missing pieces to this puzzle for doing memory devices, is having your caches coherent with write operations to the actual memory devices, and that's being addressed by other standards. NVMe was a sort of a rethink of how we do storage. With SATA and SAS, we're just not able to, or at least SATA was not able to keep up with the speeds of the new flash devices. So NVMe was formed to try to solve that by creating a PCIe-based standard that provided for fast access to these devices and low latency access to these devices. But because they were PCIe based, that meant that you could switch them, which meant that you could put them in closures and connect them with a PCIe fabric switch and get some disaggregation even with PCIe. But NVMe didn't stop there. They added additional layered protocols on top, specifically their fabric protocols that allow you to layer NVMe on top of other fabrics, such as RDMA or fiber channel, and even now TCP. General TCP is a fabric for NVMe over fabrics. So this allows our storage world to be fully disaggregated. Now we're going to enter into some of the protocols that are being designed right now. They've actually been in the works for several years, heading in this direction to be able to disaggregate memory and I/O devices. One of these is C6, which is the Cache Coherent Interconnect for accelerators. With its key members being AMD and ARM. Huawei, Mellanox, Qualcomm, and Xilinx. It's an open protocol, open standard rather, that dictates the hardware as well as the signaling. It provides cache coherency in the hardware layer between the devices that are connected via C6. And C6 used PCIe and basically added the cache coherency layer on top of it. So all of the existing PHYs and signaling and interconnects are PCIe, so it gets to leverage that wealth and broad support of PCIe, but allows you to start considering disaggregating memory devices and persistent memory devices as well as other I/O devices. Another one of these standards for high-speed bandwidth is Gen Z. And Gen Z had sort of much broader goals than just a high bandwidth cache coherent infrastructure. They wanted to also provide for various topologies other than just point-to-point. They wanted to be able to reach devices that may be even off-rack. And so Gen Z has designed a system that allows for that point-to-point type of coherent memory access semantics, but they also have a message passing protocol inside of it, more of a put-get type of communication scheme, as well as supporting a block interface as well. But at the end of the day, it is meant for disaggregating all the various components of a system and connecting them via this one interconnect that is Gen Z. It is based off of Ethernet PHYs, so you can have the local interconnects, but you can also have a broader range of distances that are supported by Gen Z as well. And I think this is where you're going to start to see some of the security issues start to show up. The next one is a third standard in this space. This originates from IBM and the Power architecture. Originally it was part of the Power architecture itself, but IBM has now moved it into its own open forum to allow it to be processor independent or agnostic to the actual processor architecture. Again, the idea here is to provide a cache coherent interconnect between memory and other devices. Full cache coherency is not in the current version, which is 3.0, but it is coming in 4.0, and it will be there coming soon. And there are products that support this. Power 9 has this built into into their processors right now, but again, it's meant to be processor agnostic. I forgot to also say that C6, there are products in the C6 space that support C6. I think Huawei just announced a ARM SoC that has C6 built into it, and there are other Gen Z products that are coming as well. So what does that look like? So now we have these protocols that can serve as the disaggregation points for these components, but it's all very forward-looking type of work that's going on right now. It's in the early stages, and there's a lot of software work that needs to be done on top of this. First of all, we need to have support in our operating systems for these protocols. C6 probably will get there fairly quickly because it's based on PCIe, but there's not only operating system support that's required, there'll be needing to be orchestration support as well. Still some significant work ahead of us. But there are components of these that actually exist today, especially in the storage world. I think is the prime example of where you can compose storage subsystems today, and more products are showing up on the marketplace for that those kind of features. And that's where I'll hand it over to Alex again to talk about some of that disaggregation that's going on in the storage world.
Thanks very much, guys. Just got a couple of questions, and I know Mike was interested in one of them, which was to do with security. The question is said, I'm just going to try and find the question again. It said, in composable environments, how does security scale with it? Specifically encryption, do you have to encrypt everything? I know that Philip alluded to part of the answer, but Mike, you wanted to add something?
Yeah, thanks, Alex. What I wanted to add to what Philip said earlier was this concept of orchestration. I mentioned earlier that orchestration requires the ability for some software layer to collect attributes, and those attributes can be the requirements of the application and the capabilities of the underlying components to deliver on those requirements. So if an application requires a level of security, and use encryption as an example, the orchestration layer needs to interpret, are those data at rest encryption requirements, in which case the storage components that it orchestrates need to provide that data at rest encryption. Are they data in transit level encryption capabilities? Then it needs to orchestrate a network that provides the data in transit encryption. So that's at the application layer, and I think the question was focusing on jobs, but I'd say in the early phases it's going to be for a particular application, what are its basic requirements, and do the components that are available out on this pool of resources on the network provide those attributes that meet the requirements. So it's,
okay, yeah,
that's a higher level initially. Potentially later there could be the ability to break this down.
Yeah, that's a capabilities and orchestration question, isn't it? Where you actually describe the capabilities of the underlying infrastructure, and then the orchestration deals with orchestrating the right components together. So one of the other questions that came through really quickly was about latency, and that actually always fascinates me as well. You know, I was always told bandwidth is an engineering problem, but latency only God can fix. And we've got a question here, for pooled memory or memory from different racks, for example, what about latency? You know, local memories don't necessarily have the kind of latency issues. Is that where cache coherence comes into it, Philip?
Absolutely. Yeah, I think you can. I think you can safely say that there will be, always be local memory around our processors for latency and performance issues. But I would also say that we've also seen that there are applications out there, especially for I/O, being able to fill memory with data from I/O devices. Those kind of latencies implicate how fast you can get at the data anyway. So there's a whole spectrum of latency requirements. Your programs the executables are going to require very low latency, but I may be able to tolerate slightly higher latencies for other type of memory accesses, depending upon what I'm trying to get at. And if I can, consume different portions of the interconnects to deliver from I/O devices to these pooled memory devices, then I can free up bandwidth for using it for other purposes as well. So you're definitely right that you will see latency issues, meaning that there are differing classes of latency that you'll see with different devices, but those become part of your palette, if you will, about designing a system and figuring out what you need and what you can leverage inside the system. So, I think you're exactly right. The farther away you get away from the processor, the more latency you're going to see. But in some cases that may be okay, in other cases it may not, and you will design and be able to orchestrate based upon these, what the application needs and attributes of the underlying component, what you can use and what you can't use.
Okay, thanks. So I'm going to wrap up here by talking a little about some of the newer storage ideas, and Philip, who is our speaker today,
Excuse me?
Devices are autonomous, disaggregated, and composable storage devices. And if you think of worker ants, and if you think of ants with specialized capabilities, this is exactly what it's about. We can have devices that are good at doing backups. We can have devices that are based on flash technologies. And I'd strongly recommend you go out and look at this paper, because it also contains a sort of, it's a movement about disaggregation. It's not really about composability per se, but it's another dimension to the way that we're beginning to look at storage devices, and we're beginning to draw them together in terms of what the application requires. And I'd strongly recommend you go and look at it. The link is actually at the bottom of the slides. By the way, I will be posting a PDF of the slides very shortly, just before we exit. So new ideas on new social. Strongly recommend you go and read that, because this is really coming. These are ideas that are coming to fruition now. The other thing I'd like to point out is that although we're talking about stuff that appears to be really perhaps more focused on certain types of applications, the applications we're traditionally involved with, where we might have used aggregated storage and NASs or SANs, and today we're talking about scale-out or hyperconverged. This tomorrow picture of having pieces connected to a common bus is going to be driven a lot as well by IoT, the Internet of Things. If you think about composability from that aspect, if you think about having millions to billions of devices that you need to pull together in terms of an application, then this kind of thing is equally applicable to them. So this is not just for your big data center applications where everything's within feet. This could be much larger, widespread applications where things are geographically spread out. And the idea behind this is really simple, and the guys have already explained it. This is about all these elements being able to freely talk to each other, and also having pieces that allow us to do the composition of it. And apologies, by the way, I understand you may have lost me very briefly. I do apologize. So, thank you for attending today. What's coming up? Well, we've got a new webcast coming up very shortly called What's New in Container Storage. This is with a member of Docker Inc., Keith Hudgens, who has presented for us before, and he's going to bring us up to date on exactly what he's been doing in the Docker container world. And it's something we're beginning to take more interest in as well. Here's another aspect of orchestration that we're pursuing as a group here and providing with education on. And last but not least, you should be able to rate this webcast on the way out. Thank you very much for your attendance today. I'm going to put the PDF up pretty shortly. Just let me find the address. Got it here. I'll put it up for you. You'll find it on the website. Please rate us on the way out. Please give us a score, 1 to 5, whatever you feel is appropriate, and give us the opportunity to understand why you give us that score by putting a comment in place as well. So you should have now that link, and the full Q&A from the webcast will also be posted. In the meanwhile, I'd like to thank both Mike from Caminario and also Philip from UCSC for talking to us today and giving us this real insight into where this industry is going in terms of composable infrastructures. And if you have any questions, please come back, address them on the website and on the blog, and we can answer them for you. But in the meanwhile, thank you very much, and have a good rest of your day.
Thanks, everyone.